Hello everyone, I'm Zeynep Ergin. I'm a freshman electrical and electronics engineering student in Bilkent University, and today I'm going to present you all my Physics 102 lab project, which is about induced electromotive force by Faraday's law. And the aim of my experiment is to test Faraday's electromagnetic induction law by analyzing the change in induced EMF for different number of turns and coil areas. Faraday's law basically shows that whenever the magnetic flux through a conductor changes, an electromotive force is induced in that conductor. Here is the formula for electromagnetic flux through a surface S bounded by a loop. As you can see, it is related to the magnetic field and the area of the loop. When we take the time derivative of the previous equation, we end up with this. And Faraday states that the induced EMF in a single loop is proportional to the negative rate of change of the magnetic flux. Lenz's law explains the negative sign in the equation by stating that the induced EMF acts against the flux change. As for coil width and turns, the total induced EMF can be shown with this equation, since in the experiment the angle between the loop's normal vector and the magnetic field will be 0. The equipment I have used for this experiment are coils with 2 cm of radius which have 20, 30, 55 and 80 number of loops, coils with 1.5 to 4, 6 cm of radius which have 20 number of loops, crocodile's cables to connect the coils to the multimeter, a strong magnet, a measuring tape to determine the height which the magnet will be dropped from, a multimeter, a ruler to measure the radii. First, I measured the EMFs related to the number of turns. I dropped the magnet inside the coil and the distance between them was 20 centimeters and it was consistent for each drop. I repeated the measurements 3 times for each coil to ensure the measurements were consistent. Here you can see the results I have obtained. For the next part of my experiment, I looked into resulting EMFs related to the different radii. I followed the same procedure as before, and in this table you can see the results I've obtained. Then I plotted these graphs. The red line in the graphs gives us the theoretical values for EMF, and the blue dots are my experimental values. As you can see from the first graph, it shows a linear relationship where the induced EMF increases proportionally with the number of the turns in the coil, as predicted by Faraday's law. And the second graph shows a parabolic relationship with the induced EMF increasing more rapidly as the radius of the coil grows. This is because of the area of the coil, which is proportional to the square of the radius, influences the induced EMF. Later, I calculated the percentage errors for each dataset. Since there isn't a proper relationship between the error rates, it can be said that the errors were most probably random. For the changing number of turns, the error rates are pretty low, average of 5%. As for the changing radii, it's a bit more higher, which is around 11%. Overall, we can say that the experiment was successful since the error rates are low. And the reason for these errors might be due to measurement inaccuracies with the tools and misalignments in the magnet's positions during the trials. Parallax errors might have also occurred while measuring the radii and coiling up process, since counting the number of turns was pretty hard. Additionally, the experiment was done in a lab environment and there were other magnets around, and this might have caused some external magnetic interference. To reduce these errors, more precise measuring instruments could be used, more trials could be conducted to ensure consistency in the results, and the coils could be aligned more properly. If we ignore the errors, we can conclude that the induced EMF rises parabolically with the coil radius and linearly with the number of turns, proving Faraday's law.